So we've been working on a kind of alluded to this already. We've been working on a few little small projects in our launch phase, I guess, while we're still looking at recruiting staff. So a group of my students actually, we recruit a couple of days a week to support us, have pulled together some bits of study. So they've asked me to present on their behalf today. Anyway, so we've got some initial exploration on a couple of small projects, which I will briefly go through before we go on to have a short break before I hand over to the headline act. So in additive manufacturing, powder bed in particular, powder cost gets a lot of press as a restrictor for additive, and it's not to say that that's not true. Any feedstock can be quite expensive, and the reality is for additive powder bed fusion in particular. High value manufacturing, does that mean that there's automatically a high cost of the final product and therefore high feedstock costs? I guess there's a little bit of that part of it. When we'll hear much more on feedstock tomorrow, but when we're manufacturing or making powder, atomizing powder, the yield, which is of the highest value, I guess, for us as in laser powder bed fusion, is minimal. Beyond that kind of sweet spot, that laser powder bed cut, it's not always usable if it's a new material or if it's a relatively niche material. Use material like scalp alloy, for example. There's not lots of use for the other sizes that are natural as part of the atomization process. So that if the laser powder bed cut gives us a best all-rounder, and it's popular because people want it, and people want it because the machine vendors tell us that's the powder to use, then it will make it expensive. Yes. Does that mean that large powder is not processable? Is it worth looking at? We decided to start some small exploration in this field. The main reason for the project is because the bigger picture is some products like titanium, for example. There's maybe some really interesting opportunities. We did the project in terms of a short run just with a 316 steel. So what we had was a standard 15 to 45 micron cut. We used our standard parameters, our exact metal XM200C, 30 micron layers, and we did as I call it, a standard density cube build, the builds that you've probably seen hundreds of times. Because of the nature of our investigation methods, let's say, we wanted to use PIP, which we've now heard lots about and we hopefully understand. So we didn't need to do large full height builds. We could go for a short build, so we could do a quick turnaround time. So I think it was about 2.5 hours for the build, about 25 minutes per coupon before we got some test data. We then also looked at a large and oversized cut, so a 45 to 150 micron cut. And all we did just for the quick experiment was we doubled the layer height, and then we calculated energy density to create a sweep of different opportunities. So three powders. So I think the 15 to 45, I think I explained that. The other two were an energy density sweep. And we're just looking for some correlation between energy density and mechanical performance, I guess, 60 micron layers. What we tried to do was create a 50-50 blend, so we then cover 15 to 45, 50% plus 50% of the 45 to 150. Same builds in all cases, and it was a first dip check. This was only completed a few days ago, so there's still lots of work to be done. But in terms of our method of analysis, we have the granule tools, granule flow, granule drum, granule pack equipment. So we started off when we ran through the granule flow with all three powders just to look for the response that we'd get. So the granule flow, granule drum, granule pack, for those who haven't heard of them, we have the flow rate. The granule drum will talk about the cohesive index, and the granule pack is the packing density. But they provide nice data for comparisons out the back end. It's a digital process, and as part of our plan at the Centre for Advanced Manufacturing, if we have our powders monitored pre and post build consistently, the value in the granule tools equipment is quite high in terms of giving us lots of data which will link to cause and effect of failures in builds by what our powders are doing. Perhaps unsurprisingly, for anyone who's worked with metal powders before, the larger powder flowed much quicker. In terms of the granule flow, we have multiple size of apertures, so it's the same test, just in different powder conditions. The blended powder was much slower and actually had, I guess, a worse fit in terms of following the trajectory expected. 15 to 45, relatively slow compared to the quick powder. It's not really too pioneering at that stage. We then looked at the granule drum. So the granule drum, in this case, we looked at low speed performance at 2 up until 10 RPM, and then 10 on the way back down to 2. And what it actually will do is the drum will start to rotate, and it will measure the angle in which we start to see powder fall. So that's one of the initial parts. Our calculation in the background will then give us a cohesivity index, and it will start to talk about whether the powder has behaviors, shear thinning, for example, where we start to see powder change with speed, whether we see any hysteresis, where we have different performance on the way up to on the way down. And again, perhaps unsurprisingly, we see a nice clean graph on the large powder. Powder dynamics of large powder is expected to be a little bit better, I would say. If we just zoom in, what we see in terms of the 15 to 45 microns is quite an interesting powder, which actually certainly starts to show some potential shear thinning when the speed starts to increase, and the reality is the next stage of this powder test should be to test at a higher speed, more indicative of what we will see a Ricotta kind of acting on a powder. We also see some differences between the speeds on the way up to the reverse speeds. Quite a sticky powder, I would say, quite surprisingly. Our Scalmaloid tests recently were very, very sticky, and that shows quite clearly in terms of the large powder. Relatively predictable, let's say. So predictability is a nice word to be able to use with metal AM. The blended powder has the best of both worlds. There's some predictability, but some quite strange behavior in terms of the way that the powder was starting to act as the speeds increased up towards 10 RPM. What does that mean? It means that larger powder is having an effect on flowability, but it also means that the blend is potentially starting to become less cohesive and therefore easier flowing at higher speeds. Again, there's an additional test to be done here, maybe looking at up to 20 RPM. So if we start to look in all cases, there certainly seems to be a potential start of some shear thinning. We can see that from the way that the graphs are all starting to try and turn down, and in this case, this is slightly distorted. What the granule drum looks like, so the top image in all three cases is the after initial settle. So you load the powder, the machine will then do an initial calibration and create its horizontal level before it then starts to rotate. And at the end of its rotation up to 10 RPM and then back down to 2, it will then go back to this horizontal position. And what we can see is an idea of whether the powder's sitting as you'd kind of expect, I guess. So again, the large powder mounted in the center, and then at the end, relatively flat. The 15 to 45 shows there certainly is some cohesivity. There's something causing some kind of clumping, and then the 50-50 blend kind of in between the two. Again, it's an informative data point in what we'd expect to see with powders. And then finally, for the granule packing density, what we actually see is the peak, which again we potentially need to go back and we do some more packing. It looks like the trajectory is showing it's not quite flattened out yet, so we're ready for potentially a little bit more packing. The 15 to 45 give us 5.11 grams per milliliter. The 45 to 150, the largest powder, had the lowest packing capability. The blend gave us the best overall because there was such a large variety of powder sizes in there. So 15 to 45 was slower flowing than the 40 to 150. with the 50-50 being the median. Expected outputs, I would say, but there were some interest opportunities, I think, in terms of the packing of the blended powder, which would give us some confidence that a nice packing would give us a nice powder bed, and if we get the parameters right, we would therefore have a relatively high density part at the end. So we ran through the powder trials, and then we went into print, so the density cubes, as you'd expect, the 15 to 45 on the left. The 45 to 150, we had some issues with the support parameters, so we ended up going down the route of printing a column at a time just to stop us having distortions in the powder bed. And then we went through the process of creating a quick baseline. So the baseline we chose was a 316L from ASM, less than 217 hardness, 40% elongation, and then a 170 to 485 yield and ultimate tensile strength. In terms of the powders, relatively surprising that we were very in the energy test by changing the hatch distance and scan speed, and across the board there seemed to be some relatively okay looking results. I ordered a balance to do density measurements in July, but it still hasn't arrived, so we haven't been able to add that data to this yet. But in terms of an initial dip check with using PIP, we managed to quickly take coupons. We tested them in the XZ plane after a quick skim and polish. Had a couple of gaps because of some issues in terms of how flat the coupons were in the end. I think we maybe were a bit overzealous on the polishing, and we didn't have the squareness that we'd need to get those data points. But generally speaking, there seems to be some performance consistency between our 15 to 45 trial and our 50-50 and our 45-150. Accumulating that together, that variable energy density trials looked like there was some consistency, as I mentioned. In the vast majority of cases, we were exceeding the ASM baseline, pre-heat treat, and etc., etc. But ultimately, gave us a bit of a positive first trial. So go back to those initial questions. That problem statement is large powder processable. And what effects will it see? Well, is it processable? It absolutely seems to be. We didn't need to go to a 6 to 9 month parameter trial. This was a few days work, which we managed to produce some meaningful data. Would we want to? I don't see why not. Geometric performance seems to be acceptable. Density cubes only. Service condition is a function of design requirement. So if you need an optimal surface finish, then maybe you would choose a different powder size. But if that isn't part of your parameterization, or if it isn't part of your need, for example, if a part will be machined all over, then maybe we do have alternative options to start to build this data set on using different size powders. Mechanical performance is promising start. There's certainly lots of data missing that we need to add over the next few months of 2023. The timing process is a small change in our machine, but if you were on a much larger machine with much larger layers, there is certainly a deposition rate benefit, I would say. In terms of cost, quite a few words there, but the hard hitting answer is titanium in laser powder bed cut versus an oversized titanium. I've only got one quote, but I got one quote to do a quick check, and the oversized titanium was a fifth of the price. So if we could create parameters that allow us to push that, and then can we potentially add value by using low cost but high value materials like titanium on a low cost machine like the Exact Metal XM200C, and can we really start to add value? And I say we certainly can. It's a promising start, and when we talk about industrial relevance, and my old Airbus colleagues, and I know there's other people in the audience today who've got extensive aerospace experience, some of this won't sit too well with your aerospace hats on, but there's a lot of industries who could benefit from the use of titanium who can't afford to go down the route of laser powder bed tie on a $600,000 plus laser powder bed machine. Accessibility of AM is really important. We mentioned that at the start. So this is one of the areas that we've been looking at in terms of large powders. The second trial that I'm quickly going to go through is our wire arc additive trial. We looked at a couple of geometries, a couple of angles and shapes, and the idea was that these would be converted into a combination of some pip coupons as well as some tensile standard ASTM-E8 coupons, thin wall, thick wall, different geometries, and we wanted to then do some cut-ups and do some initial trials. Unfortunately, the build had to be stopped relatively early, so we didn't get the Z height that we needed to be able to do the ASTM-E8 type coupons. But in the art of making sure that we had data ready for today, we went on and we did a pip overview. So focusing on the cone and this section at the top, these were meant to be cylindrical Z height tensile coupons. We managed to make some small fractions. So taking a cut as per the dashed lines give us something that looked a little bit like this. We tested twice in the substrate, twice at the interface between substrate and the first weld, and then using pip, though it isn't 100% precise, we tried our damnedest in terms of with WAM. It's much easier to do it with WAM than it would be to laser powder bed, to try and test the interface or the weld interface and also test the bulk material. So we managed to try and get some data to look at the substrate versus the interface between substrate and welds, and weld one, if you like, the bulk material, and then the interface. So again, looking at the weld performance. And the idea is with WAM that we should see the interface should be as strong or potentially stronger than the bulk material. The use of the substrate is a key part of minimizing material waste. So again, we should have similar performance. In the case of the large cylindrical part, quite a lot of distortion on the build plate. It was an inch thick substrate as well, which was we still have some significant distortion. Though I do believe that the organisation who helped us out with this, they did find that there was a couple of parameter issues in that part in the end. But we did see quite severe anisotropic performance in those interfaces in particular. We also have quite a different performance as we move up from the substrate into the weld material in both cases. That substrate variability, when you look at the different performances from the substrates of the two parts, potentially is because of the thermal effects of that cone, that large cone area. The precision indents that we are proposing we took, we don't have 100% confidence, but we are relatively confident that they were indicative of those areas. There certainly seems to be a little bit of a trend showing that maybe there was peak performance is layer one, but it certainly gave us some food for thought in terms of WAM and the potential that we should increase this study to make sure we do get these full Z height coupons. We do get the ASTM-E8 standard tensiles and micrograph performance as you would expect, I guess, in any industrial sense, and then keep looking at the pip versus tensile debate in these parts. Performance was quite good, I would say, quite consistent in many areas to what we would expect to have seen from the laser powder bed. So there was nothing too alarming, but there was quite a lot of variability in hardness. And again, there was always a chance that that's down to the coupon itself. Maybe a heat affected zone from YEDM wasn't quite removed. Certainly some additional work to be done. We only managed to get the data fully completed just yesterday, so this is one to be continued into January as we do a little bit more exploration into that field. Okay, I am relatively on time considering the drop-offs, and I know there's a lot of information in a short amount of time. Does anyone have any questions? A joint program to develop standard. Yeah, I think the Granutools equipment is a really interesting set of equipment for me, and I think there's certainly some interesting opportunities to look at a more standardized approach to testing by using that equipment. The dynamic powder analysis I think it's really powerful thinking about how do we analyze our powders in a method which is more indicative of how they would behave if they were put through our additive machine. So the dynamics of the drum in particular, the flow, I'm really confident that as we build up our data and our understanding and the kind of full process monitoring of powder pre and post build, the build success, the potential opportunity for us to do some in-process monitoring, etc., etc. I think there'll be quite a compelling case for how powerful that software will be and the reporting of the outputs of the Granular Tools equipment. So I certainly believe that's the case. And I believe the Granular Tools team have had some conversations with the ASTM. I think the reality is, like all new technology, as we've just heard from Plastometrex, it's about trying to make sure we build up the confidence. But there's certainly some interest on my side.